Hello. We're now starting Module 3. This is material out of chapters 16 and 17, and it has basically nothing to do with anything that we've talked about so far. So that's going to be the nature of the course. It jumps around quite a bit. The topics in the course, though, were chosen for one or both of two reasons. One is that the mathematics involved is relatively recent. By recent in mathematics, we mean within the last 100 years or so. And the other possible reason is that it is very widely used. And so this particular topic on computer mathematics, codes, and transmission of information has both of those characteristics. It is new because computers haven't only been around for 50, 60, 70 years, and it is very widely used because computers are everywhere we look. In fact, there are many places where we don't see them, but they're still there. For example, here we go to the grocery store to buy some ice cream. That sounds like a great idea, and on the back there's a UPC code, Universal Product Code. You take the ice cream, you walk up to the cash register, and of course it's scanned by a laser. And the computer that the laser is connected to reads these bars and determines what the product is and what its price is. Or if you look on the back of your textbook or in your textbook somewhere, there will be an ISBN number, an International Standard Book Number. And those are used for similar purposes to help identify a particular book so that a computer laser scanner can read them, and this helps with keeping inventory and tasks like this. We count on products being scanned correctly. You take this ice cream up, the scanner goes bing, and you count on the fact that the ice cream has been priced correctly. But do computers ever make mistakes? Do scanners ever make mistakes? The answer is yes, they could perhaps. The physical bars could be a little distorted if the package is flexible, for example, and things have gotten warped. Or there might be some, if this is ice cream, there might be some frost on the bars. Or maybe the scanner is out of alignment. So it is possible for a scanner to make a mistake. That wouldn't be good. Either the merchant or you would have gotten a bad deal. And so codes like this, Universal Product Code in this case, have built-in error detection schemes. So identification numbers are supposed to do two things. One is uniquely identify the product so that no two items in the grocery store have the same UPC number. And second of all, provide the opportunity to detect errors. So if the scanner detected an error, it might just beep and ask you to rescan the item. Let's look at the mathematics behind this error detection scheme. We'll get back to UPC after a while, but let's look at ISBN right now. There are actually two schemes, ISBN 13 and ISBN 10. Let's look at ISBN 10 for the moment. It consists of a 10-digit number. The positions of the numbers have various functions: language of publication, who the publisher was, the distinguishing numbers for the book itself, and then the last digit is a check digit designed to catch errors. Let's look at how that works. In this case, there are 9 then information digits and 1 check digit. Alright, for a system of labeling, let's agree that an ISBN, which has 10 digits, will be labeled A1, A sub 2, A sub 3, up to A sub 10, so then I can talk about A sub 7 without having to specify what that digit is, and I can talk about it in the general case. It's just using 10 variables to stand for the 10 digits of the ISBN. And the first 9 digits, A1 through A9, are derived and determined by the information of the book itself, and then the check digit is chosen so that this quantity is divisible by 11. This is a sum. You see various terms being added together, and it's a weighted sum because in front of the A1, A2, A3, and so on, there are various coefficients, fixed numerical coefficients. Notice the pattern goes 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. It turns out then that valid check digits are either 0 through 9, or maybe it would have to be a 10, but a 10 is not a single digit, and so ISBN 10 uses the symbol X as well. If the check digit would have to turn out to be a 10, then the symbol X is used instead. Let's look at an example, several examples actually. Is this number a valid ISBN 10? Well, what I'm supposed to do is compute this weighted sum. So here we go. 10 times the first digit. I'm looking at this. It's 10 times the first digit plus 9 times the second digit plus 8 times the third digit and so on. So 10 times, I'll put a dot for times, the first digit is a 0, plus 9 times the second digit is a 7, plus 8 times 1 plus 7 times 6 plus 6 times 7 plus 5 times 4 plus 4 times 9 plus 3 times 8 plus 2 times 2 plus 1 times 4. All right, it's a lot of arithmetic here, but it is just arithmetic. You can work out that this is 243. You can use your calculator for all of these types of calculations. And you can check that 243 is not divisible by 11. What does that mean? Well, the question is this a valid ISBN 10 number? If it were, the check digit would have been chosen. The check digit would have been chosen so that this sum we just computed was divisible by 11. If the sum isn't divisible by 11, then it must not be a valid number. So what happened? Well, the original number must have been different, and then maybe somebody was copying this by hand and made a mistake and miscopied one of the digits. Or maybe a computer was scanning the barcode and the computer made a mistake and the digit got changed that way instead. At any rate, something happened. This is not a valid ISBN. Let's look at the second question. A book is to be numbered, and so here are the 9 information digits, and now we have to add a check digit, and the question is, what should the check digit be? Okay, let's work out the sum for this. So it's 10 times 1 plus 9 times 4 and so on, plus 8 times 2 plus 7 times 9 plus 6 times 2 plus 5 times 0 plus 4 times 9 plus 3 times 0 plus 2 times 0 plus 1 times. Okay, we are trying to decide what the ISBN check digit should be. Let's let a variable n stand for that right now. And then the sum, the weighted sum, finishes with plus 1 times n. And our job is to find n. Let's go ahead and simplify this. The last term has a variable n in it. The first 9 terms do not, and so this can be combined to a single number. If you work out what that is, it's 173. and then the very last term can't be combined yet. It's a plus n. Now, we need to choose the check digit so that this sum is divisible by 11. And there are only 11 possible choices. N could be 0, it could be 1, 2, up through 9, or it could be an X standing for the digit of 10. Let's make a table. This is N. This is 173 plus N. Now, I'm going to take the values of N one at a time. If N is 0, then 173 plus N is 173. If N is 1, then 173 plus N is 174. If N is 2, then the sum is 175, and so on. 176, 177, 178, 179, 180, 181, 182, 183. And now let's check whether these are divisible by 11. So I'm just actually going through with the calculator, taking each of these numbers, dividing by 11, and seeing if the quotient is an integer, seeing if the division works out evenly. And it turns out to be no, 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 yes, no, 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 no. Okay, I want this sum to be divisible by 11, and so there is only one possible choice for the check digit. Choose n equal 3. Notice that that's the only possible choice. None of the rest of the possibilities are divisible by 11, and that will be the case. The check digit scheme has been carefully chosen. Somebody didn't just choose this 10, 9, 8, 7, 6 pattern randomly. They chose it so that there is only one possible check digit that gives a correct number, and the coding scheme also has other desirable characteristics, as we'll see a little bit later. Okay, the third question: what is the missing digit in the ISBN 10 and this number? So again, let's let a variable stand for the missing digit. Say n. Let's go ahead and compute the weighted sum. So 10 times 0 plus 9 times 0 plus 8 times 7 plus 7 times 2 plus 6 times 3 plus 5 times 2 plus 4 times 5 plus 3 times, and now we're to the spot that we don't know yet, so plus 3 times n plus 2 times 9 plus 1 times 0. Okay, there's one term right here that has an n. The rest of the terms are all numbers that can be added together. So this is 136 plus 3n. And we want to choose n so that this is divisible by 11. Alright, I could do exactly the same thing as I did up here. Make a table for the values of n between 0 and 9 and then the x. Compute the value of 136 plus 3n for each of those cases. Go through and check which of them are divisible by 11, and I would find out that there is exactly one possible choice. Here's another way. I'm not sure it's any easier or any shorter, but let me show it to you and then you can take your pick as to which you prefer. Notice that n is greater than or equal to 0, and so 136 plus 3n is going to be greater than or equal to 136. Let's try and find about what this corresponding number is going to be. Let me take 136 divided by 11 and I get 12.36. So, for example, this tells me that n can't be 0, because if it were, then the sum would just be 136, and 136 is not divisible by 11. But this tells me more than that. This tells me that the ISBN is likely to be somewhere around 12 times 11. In fact, it's likely to be, or it will be, a little bit bigger than 12 times 11. So let's list some possibilities. 12 times 11, in fact, is 132. 13 times 11 is 143. 14 times 11 is 154, and 15 times 11 is 165. Now, the question is, which of these numbers could be the sum? These are numbers that are divisible by 11. I've constructed them to be multiples of 11, so it's kind of tackling the problem the opposite direction. Here we computed the possible values for s and ask which of them are divisible by 11. Now I'm computing multiples of 11 and asking which of those could be possible values of s. Well, I know it's not the 132 because s, as we said, is greater than or equal to 136. So what if it's this? What if, so here I'm just going to set 143 equal to 136 plus 3n and see what value of n would work. If I solve this, take 143 minus 136, divide by 3, I get n equals 2.33. Well, that's not a possible answer. N is a digit between 0 and 9, or possibly the x, the 10, but it's not 2.33. So let's try 154. What if that is 136 plus 3n? What could n be? Take 154 minus 136, divide by 3, and you get n equals 6. Aha! The 154 then is a multiple of 11, so it's divisible by 11, and it is of the form 136 plus 3n for n equals 6. And so here's the answer to the question. The missing digit in this ISBN must be a 6. Notice what that lets me do. Maybe I'm reading off this ISBN off of a sheet of paper and this digit got smudged out and I can't read it anymore. Well, from the remaining digits I can actually go back and reconstruct the fact that it is a 6. So there's redundancy built into these identification numbers, so you can make a mistake, at least a small mistake, and still be able to recover. Let's look at ISBN 13. So here it's a 13-digit number. We'll number them A1 through A13. And the check digit is chosen so that the following weighted sum is divisible by 10. So remember, ISBN 10 used divisible by 11. ISBN 13 uses divisible by 10. And instead of going 10, 9, 8, 7, 6 in the weighted sum, this goes 1, 3, 1, 3, 1, 3, 1, 3, and so on. So question, here's an ISBN 13. There's a missing digit here. We want to know what it is. Tackle the problem in a very similar way. Let n stand for the missing digit. Compute the weighted sum. Be sure to use this pattern now. So it's 9 plus 3 times 7 plus 8 plus 3 times 0. Every other term gets a 1 in front, and then the opposite terms get 3's in front. So now plus 3 plus 3 times n plus 1 plus 3 times 6 plus 4 plus 3 times 4 plus 9 plus 3 times 9 plus 2. All of the terms except 1 are constants. They can be added together. This is 114 plus 3n. And notice this is even easier. Maybe you thought the ISBN 10 was easy, maybe not. ISBN 13 is easy. To be divisible by 10 just means that the number ends in a 0, right? And numbers that end in zeros are really easy to think of. So I want this sum to be a number ending in 0. I know it's at least as big as 114 because 3n is greater than or equal to 0. So if I start listing nearby numbers that are multiples of 10, like 110, 120, 130, and so on, it's obviously not 110 because then n would have to be negative. Can it be 120? Well, what happens if this were 114 plus 3n? What would n be? 2. And that does it. The only possible choice for this missing digit is a 2. Otherwise, it would not be a valid ISBN 13. Okay, let's talk about catching mistakes. There are two kinds of errors that are fairly common. One is a so-called single-digit error, and we've been discussing that. What happens when you're copying the ISBN and the number was, say, a 6 and you copy it as an 8? Can that error be caught? The answer is yes. Another type of common error is to transpose two adjacent digits. So suppose this is the actual ISBN 13 for a book. And a librarian is copying this number by hand or maybe scanning it, and somehow by a computer laser, and somehow two digits get swapped in their position. If you look at it, the 1 and the 6 interchanged positions. Everything else is the same. Well, can this error be detected? Let's check. First of all, let's verify that this original number is a valid ISBN. So check original number. That would mean to compute S equals, here we go, 9 plus 3 times 7 plus 8 plus 3 times 0 plus 3 plus 3 times 2 plus 1 plus 3 times 6 plus 4 plus 3 times 4 plus 9 plus 3 times 9 plus 2. The pattern 1, 3, 1, 3, 1, 3 on the coefficients, and then reading off the digits in the ISBN in order. This works out to be 120. So this number is valid. The problem told us that it was, but I was just double checking, and then I want to use this sum to compare. Now, check the miscopied number. So here I'm going to compute S. I'll put a prime on it. This is going to be a different number probably, but it's computed with the same scheme. 9 plus 3 times 7 plus 8 plus 3 times 0 plus 3 plus 3 times 2 plus 6 plus 3 times 1 plus 4 plus 3 times 4 plus 9 plus 3 times 9 plus 2. This works out to be 110. Question: will this error be detected? Well, the way the computer is going to check this ISBN that it receives is to compute this sum that we called S prime and say, is it divisible by 10? If so, yes, it's a valid ISBN. If not, no, it's not a valid ISBN. So if this is actually a mistake, you want it to be caught. You want the computer scanning it to say, no, this is not a valid ISBN, must have been a mistake. Then we can go back and talk about what the mistake might be, but at least we'll catch it. In this case, though, the computer's going to say, this is a valid ISBN, but it's not the right one. It wasn't the one that was originally sent. And so, since this is a valid ISBN, the error will not be caught. This is unfortunate. We would certainly like our computer scheme to catch errors and be able to keep us from reading a code wrong and then pricing somebody's groceries wrong or ordering the wrong book. We're not going to be able to do that, it looks like, with this scheme. So the question becomes, when does this happen? Can we predict when a ISBN error is going to be caught and when it might not be caught? So let's look at the scheme behind it and see if we can tell whether I'm plugging in the power supply on my computer, if you wonder about the mysterious noises. So let's look at the scheme and see if we can poke around in the theory a little bit and see which errors will and will not be caught. We're talking about transposition errors here, which is 2 digits got switched. 2 adjacent digits got switched, in fact. So, to answer the second part here, suppose M and N are adjacent digits that got switched. We know that we're not always going to catch those. Again, when we switch the 6 and the 1 here, we were not able to catch that. But maybe sometimes we can catch these transposition errors. Notice the similarity in the pattern. This had a 1 plus 3 times 6. And this had a 6 plus 3 times 1. So that piece here added up to 19. That piece here adds up to 9. And the reason that this error wasn't caught was that 19 and 9 are sort of alike. When you're checking divisibility by 10, they differ by 10. So if you take a number that's divisible by 10 and you add 10 to it, that new number is also divisible by 10. And so the key is whether the numbers that were switched did so in a way that makes the sum S change by a multiple of 10. It's kind of unlucky that it did. It could have been, these could have been different by some other quantity than a multiple of 10, and then we would have been able to catch the error. So notice that this has a pattern m plus 3 times n, and this has a pattern n plus 3 times m. When two adjacent digits are switched, one of them had a 3 in front, and then after the switching, the other one did. So when will m plus 3 times n and n plus 3 times m differ by a multiple of 10? These are exactly the cases that are not going to be caught. So let's compute how different these two numbers are. Different means subtraction. So what happens when we take m plus 3 times n minus n plus 3 times m? Let's do some algebra. This is m plus 3 times n minus n minus 3m. And that is minus 2m plus 2n. And that is minus 2 times m minus n if I factor out a negative 2. Okay, the question then is, when is this a multiple of 10? Well, here's a 2, and so this is going to be a multiple of 10 if the m minus n is the other factor of 10. What is the other factor of 10 other than the 2? It's a 5. And so answer, when m and n differ by 5, then m plus 3n and n plus 3m differ by a multiple of 10, and the error won't be caught. And that's exactly what happened in the case, the numerical case we were considering. You see, we had a 1 and a 6. Those two digits differ by 5, and so when we flip them, when we transpose them, the error was not caught. You could go back and check if this had been a 1 and a 4, say, sitting side by side, and you flip those two digits, that mistake would have been caught. So the ISBN 13 catches most transposition errors. The only time it doesn't is when you transpose two adjacent digits that differ by 5. So like a 1 and a 6, or a 2 and a 7, 3 and an 8. If those numbers are side by side and they get transposed, ISBN 13 won't catch those. Okay, finally let's talk about UPC. These are actually what are on the grocery store packages. How does UPC work? Well, it's a 12-digit code, and so let's label it A1 through A12, and it works very similar to ISBN 13. You have this 31313131 pattern, and the first 11 digits are information, what the product is, what the store is, and so on. And then the last digit is the check digit, and it's chosen so that the sum S constructed this way is divisible by 10. Let's answer a different question for UPC. One of the most common errors is miscopying a single digit. So here it is, and I've miscopied one digit. Which digit? Right here. I can't get my eye on it. Right here. It's supposed to have been 33, and somebody miscopied it as a 3.5. And the question is, will that copy error be caught? Okay, here is the UPC that we think we have, that the computer is scanning. Will it catch the error? Well, it computes S equals, here we go, 3 times 0 plus 7 plus 3 times 0 plus 3 plus 3 times 5 plus 0 plus 3 times 5 plus 0 plus 3 times 6 plus 0 plus 3 times 6 plus 0. Lots of zeros in this number. This works out to be 76. Is it a valid UPC? Same question. Is it divisible by 10? No. And so not a valid UPC. In other words, the miscopy is caught. And again, if this happened in a store, what you would probably get is the scanner would beep and ask you to rescan the product, and you may never have known that a scanning error like this happened, but at least the mistake was caught. Let's answer the second question. Which single-digit copy errors will be caught by the 12-digit UPC? So in the last example, we talked about when a transposition, when switching 2 digits, would be caught in ISBN 13. Here, let's ask ourselves which copy errors will be caught by UPC 12. So here is one that was. If this 3 were changed to a 5, we caught that error. Is it possible that we could miscopy one of the other digits in some other way and that error would still be able to slip through the computer scanner? Let's just talk about a mistake in the first digit. Here's what S looks like. And so S, I'll say S actual. It has the form, just recopying what's there, 3A1 plus A2 plus 3A3 plus A4, 3A5, A6, 3A7, A8, 3A9, A10, 3A11, A12. And now S miscopy. So I'm going to ask, what happens if I copy this digit wrong? Instead of copying it as A1, I copy it as A1 plus an error. So maybe the actual digit was a 2 and I copy a 5. In other words, I made an error of 3, the difference between what it really should be and what I copied. Or maybe this is a 5 and I copy it as a 1 and then the error was -4. So in this case, I'm going to, the computer scanner is going to compute 3 times A1 plus E plus A2 plus 3 times A3 plus, and the rest of this is exactly the same as we had before, so I'm just going to put ... plus A12. S actual is divisible by 10. It's a valid valid UPC. The question then is, for which values of E is this or is this not a valid UPC? Let's multiply the 3 through, and I'm going to put the 3 times E first and then the 3 times A1 second, and then the rest of it is just as before. So recopying part of it, put the dots to indicate I'm not filling in those terms, but we know what they are here. All right. The question now again is, for which values of E is this valid? In other words, for which values of E is this divisible by 10? Well, we know this is divisible by 10, and it's right here. This is divisible by 10 since the original UPC was valid. So then the question is, what about this whole thing? I mean the 3e plus the remaining things. Okay, think about it. You have a number divisible by 10, and now you're adding something to it. When will that entire sum be divisible by 10? If you look at an example, suppose this is like 90, and then you ask, well, what could I add to 90 to make a sum divisible by 10? The answer is you have to add a multiple of 10. 90 plus 20 is divisible by 10 because 20 is, but 90 plus 21 is not divisible by 10 because 21 is not divisible by 10. So it all boils down to whether 3e is divisible by 10 or not. Well, what can e be? E is the difference between the actual digit and the one I copied. And so, for example, the actual digit could have been as small as a 0, and I could have copied as large as a 9. In that case, the error or difference would be 9. So E is somewhere between 9 and then I could have copied a number too low. In that case, the error would have been a negative number, all the way down to negative 9. So E is something between positive 9 and negative 9. And then I'm interested in saying, when is 3 times E a multiple of 10? Well, if you just think about some possibilities for E, 3 times negative 9 is not divisible by 10. 3 times negative 8 is not divisible by 10. 3 times negative 7 isn't. 3 times negative 6 isn't, and so on. The only way that 3 times E, for E between negative 9 and positive 9, the only way that can be a multiple of 10 is if E is 0. But if E is 0, then we didn't make a mistake at all. And so if there is an error here and E is different than 0, then we're going to catch it. Let me write something down about that. This is divisible by 10, this little piece, the latter piece, since the original UPC was valid. So the error will be caught since 3e is not divisible by 10 for any e, any non-zero e in the range -9 to +9. Again, e has to be something between -9 and +9, and then 3 times e is not going to be a multiple of 10, and then a number that is a multiple of 10 plus a number that's not a multiple of 10 will not be a multiple of 10. The sum for the miscopy will be invalid and the error will be caught. What we've discovered is that UPC catches all single digit copy errors. If I make a mistake in one digit, that error is going to be caught. That's a good thing, and that's why the coefficients were chosen this way. It wasn't just A1 plus A2 plus A3. It's 3, 1, 3, 1, 3, 1. Part of the reason for that is so that we're able to catch these single digit errors. And that's the job of an identification number scheme. Part of the job to catch errors. This was all in section 16.1, and this is the only section of chapter 16 that we're going to talk about. Thanks.